This video is a proof of Pythagoras' theorem, which is discussed in more detail in the previous video, video M12. So if you haven't seen that, it might be worth having a look at that first and then coming back to this one. Now, I did say I'd give you a sort of explanation of why it works, or a kind of proof. And this diagram is something that is very commonly seen when explaining why Pythagoras' theorem works. In the middle here, we've got the white right angle triangle. We check it's a right angle. The longest side, the hypotenuse, is called C. And what we have are some squares, this blue square here, for example, with a length of side C. So the side which is actually against the triangle has a length of C, and because it's square, it means all sides, including this one, have a length of C. And that tells us, or from that we can find the area of this light blue square is going to be C squared. And it's the same for B. We've got this purple square. The length against the triangle has a length B. It is a square, so the other side also has a length B, and the area is B squared. And the same for this one here. We've got A and A, so that area is A squared. And what the textbooks would have you believe is that the area of the two purple squares adds up to the same area as the area of the light blue square. And that is basically just Pythagoras' formula. The area of one purple square plus the area of the other purple square is equal to the area of the light blue square. That is Pythagoras' formula. You should recognize that. But it's not obvious that these areas do add up. I mean, you can see that C, or the blue square, is slightly bigger than this purple square B, and you might believe that if you chopped A or this other purple square into strips and laid them round the edge, it would actually give you a total area the same as the blue area. But there's no sort of evidence that that is the case from this proof. And for that reason, I don't really like this diagram. It is true, but it doesn't sort of reveal its truth in any specific mathematical way to you when you look at it. So I'm going to give you an alternative proof. And I like this proof because it's mathematical and you end up with Pythagoras' formula exactly at the end. Didn't make this up myself. Whoever did is to be congratulated. But what we've got here is a square, the yellow square, and inside that square I'm going to draw another square, but this one has been rotated a little bit. So there we have our second square, and it's rotated so the corners are touching the sides of the yellow square. And this creates 4 yellow triangles now. Those are the yellow triangles that we see. And each of those is a right angled triangle, since we have the corners of the square here. These are all right angles. And they're all the same size, these yellow triangle. So let's label some sides. We'll have A there, which is just from the corner here down to there. B there, C there. This one's exactly the same size, so we've got an A here, B here, and a C here. And we can just go around doing all these. So here we see, for example, C is opposite the right angle there. If we add up the areas of the blue square in the middle and the areas of all of the yellow triangle, we should get the area that we started with, the big yellow square before I put the blue square in it. And that's how this proof works. So let's start working out that. First of all, what's the area of the big yellow square on its own without the blue square in it? Well, the length of a side is A plus B in each case. B plus A here, B plus A, and B plus A. So the length of one side is A plus B. It doesn't matter which way around we put it. And if we square that, we get the area of the big square. Now, this must be equal to the area of the blue square plus the area of all the triangles. So what is the area of the blue square? Well, the blue square has a side of length C in all cases. So the area of the blue square is simply C squared. And to that, we've got to add the areas of these 4 yellow triangles. Now we can do that with the area of a triangle formula where the area is half the base times the height. Let's just do that over here. Area of a triangle is half the base times the height. Now don't get confused with this B here. I'm using that to refer to base. Let's do it in capital letters to distinguish it. Base times height. And if we take one yellow square, let's take this one. The base is length B and the height is length A. So the area of that single triangle is a half A times B. And we've got 4 triangles here. So the total area of all the triangles is 4 times a half AB, and that is 2AB. So C squared plus 2AB. That's the area of the blue square, and this is the total area of all of the yellow triangles. Another way of doing the area of these triangles is simply to take 2 of the triangles and put them together. So let's say there's one, and we put the other one on top, and we see that 2 of them together have an area of AB. So if we bring in the other 2 triangles, which also has an area of AB, then we get 2AB, which is what we've got up here. So either way, it comes out the same. So the area of the blue square, which is C squared, plus the area of all of the yellow triangles has to equal the area of the big square, which is A plus B squared. So let's multiply out this bracket. We've got A plus B times A plus B, and that's equal to A squared plus AB plus AB plus B squared, and that's equal to A squared plus 2AB plus B squared. Let's just keep them separate. And that's equal to C squared plus 2AB. We just bring those ones down from there. Now we've got this 2ab on both sides of the equation, so we can subtract 2ab from both sides, and we're left with c squared equals a squared plus b squared, which is the Pythagoras formula, although it's the wrong way around. Doesn't matter, we could write it a squared plus b squared equals c squared, but this is a geometric proof of that formula because the areas do add up. And in that sense, I think it's a little bit neater than the diagram that you see in textbooks, which looks like this one, which doesn't actually prove anything to you. At least doing it this way, we end up getting the formula out of the fact that the areas have to be the same. So that's all. Goodbye.